Hi everyone, welcome to this video. My name is Shamil Alam and I'm currently a PhD candidate at the University of Tennessee, Knoxville. So in this video, I'll try to give you a brief tutorial about the HSPICE simulation tool, which is mostly used for circuit design and circuit simulation. So in this video, I'll talk about how we can perform different types of analysis, such as DC, transient, and Monte Carlo analysis for different circuits using these HSPICE simulation tools. So we all know that SPICE and Spectra are the two most famous simulation tools for integrated circuits, and SPICE has different variants. Actually, HSPICE is one of them, and in fact, HSPICE is the most advanced and most superior member of the SPICE family, which is also used by different industries. HSPICE comes in two different variants as well. One is the HSPICE, which is typically used for analog, digital, and mixed signal circuits, and the other one is HSPICE RF, which is only dedicated for the RF and high-speed circuits. So in this video, we will use the HSPICE tool and we'll show how we can use this HSPICE tool to perform different analysis for some of the simple circuits to show you the process of using this HSPICE tool for circuit design and circuit simulation. So these are some special features of HSPICE. So HSPICE provides superior convergence compared to any other existing circuit simulation tools, and that means it becomes faster to simulate any circuits and get the output using this HSPICE tool. And another advantage is that, as I mentioned, HSPICE allows different types of analysis such as DC, AC, and transient analysis, and it also allows multi-parameter optimizations at the same time, which helps us to debug any errors in the circuit design. And it also has the built-in input distribution functions that we can use to run Monte Carlo simulations, which are typically used for exploring the effects of external variation on the operation and the performance of different circuits. And it allows us to keep the worst case condition in our mind while we design and simulate these circuits. So now let's talk about the file types for this HSPICE tool. So the primary input file for this HSPICE simulation is this .sp file, which contains all the required information to run any circuit simulation. And we can open this file with gedit command in any terminal. And so this file actually contains all the required informations, as I mentioned. So these will contain the information about the any external models, library, or sub-circuits that we use in the main circuit. It will also have the information of the simulation environment that we'll use to run any analysis for any circuit. It might also have the list of parameters or variables that we use for building the circuits. Then most importantly, it will have the information about the main circuit that we'll be simulating, and there we can use different types of electrical components like resistance, resistors, capacitors, voltage, and current sources, and they are built in inside these HSPICE tools, which we can use to build the circuit that we want to simulate. And then it will this .sp file will also have the information about the analysis that we want to run. So if we want to run DC, transient, and Monte Carlo analysis, for each of these analysis we have dedicated command and methods to declare this analysis type in this .sp file. And eventually, if we want to perform any measurement for any performance metrics after this simulation or analysis, we can use the .meas command, that is the built-in function again for this HSPICE, and we can do different types of measurement there. So this .sp file will be the primary input file, which will have all these informations required to run the circuit simulation. And then when we run the circuit simulations, the HSPICE will generate the voltages of all the nodes in the circuit that we have built, and it will also store the current flow and the power consumption of every component in the circuit. And based on the analysis that we run, it will create different types of output files. For example, if we run the DC analysis, the output file that will be generated will have a .sw extension. Again, there is another option that you can use in HSPICE, which is the alter command, and there you can uh, then you can there you can vary the values of different parameters, and you can run the same simulation or same analysis with those different values of parameters. So if you have multiple dot alter command in your .sp file, it will the ACSpice will generate more than one output files, and the extension of those files will be .sw1 and .sw2 and so on for DC simulation. Similarly, if you run a transient simulation, the extension of the output files will be .tr0, .tr1, .tr2, and so on, depending on how many dot alter commands you use in the .sp file. Then this is optional. If you have any measurement command in the .sp file after the simulation, then if you do DC measurement, the output files will have .ms0, .ms1, and so on extensions. And if you have any measurement command in the transient analysis, the output files will have .mt0, .mt1, .mt2, and so on extensions. So these are the primary output files that will be generated by HSPICE, and you can open these files with any waveform viewing tools like WebViewer, Cosmoscope. You can import these output files on these tools, and you can plot the voltages of different nodes, the currents flowing through different components, and you can verify the functionality of the circuit that you have built. There is another option, which is the dot print or dot probe command here. So there, if you are interested in some of the voltages of specific nodes and currents flowing through specific components, if you are more interested about them, you can mention them after the dot print dot probe command. So what this dot print and dot probe command will do, it will create another file which will have extension of dot print sw0 for DC simulation, dot print tr0, dot print tr1, something like that for transient simulation. So there you will only have those voltages and currents that you mentioned after that dot print dot probe command. And what you can do, you can export those dot print sw0 or dot print tr0 files to any other plotting tools like MATLAB, Origin, Python, and then you can plot the voltages and currents that you get as the output there any way you want. And you can also do some analysis on those outputs using those sophisticated tools with this with these output files there. Now I'll talk about some syntaxes for this HSPICE when you create this .sp input file. The first thing to remember is this HSPICE tool is case insensitive. So if you when you define different nodes or different parameters, if you use capital and small letters to differentiate between them, that will not work, because HSPICE will consider the capital or the small letters as the same. So if you have a node name called node 1 with capital letters and node 1 with all the small letters, they will be treated as the same node. So this should be kept in mind while creating the .sp file. And then about the inputs, so the HSPICE will consider by default the SI units for the parameters and for the components that you define. For example, if you define a resistor with a 10 kilo ohm value, you'll just need to mention the value 10K or 10,000 or 1E4, something like that. And HSPICE will by default understand the unit of the resistor, which is ohm. Similarly, for capacitor, it will understand the unit, which is farad. And for voltage and current sources, it will by default understand the SI unit, which is volt or ampere. So you'll have to mention, you'll have to keep that in mind again. So when you define the values of different parameters or different components, you'll have to convert them into SI units. Then one of the major advantages of HSPICE tool is that you can include or you can use external libraries, external models for different device technologies that you can use in your circuit. So there are dedicated commands for that. So if you want to include any other SPICE file as sub-circuit or device model, you'll have to use this .include command, and then you'll have to mention the location and the file name. And then if you want to include any library, what we will do in one of the next slides in this presentation. Then you will need to use this .lib command. And if you want to use any Verilog based compact models for any devices, you need to use that .hdl command. So these are the three .include, .lib, and .hdl commands that you can use to import or use any external models, libraries, or any sub-circuit files in your input.sp file. And then you can use the star to include any comment on your code. So if you want to clarify something for yourself or for others who will be using this .sp file, you can use this star and you can write anything after that as the comment. And another thing to remember here is this: the first line of the .sp file will always be a comment. So even if you write something required for the circuit simulation there, that will be ignored by HSPICE, because it will always consider that the first line is a comment. So what you can do is you can keep the first line empty and you can start creating the .sp file from the second line, or you can write something like with the star command as well as a comment, but eventually it will be considered as a comment by HSPICE. Then you can use this dot param command to list different parameters or variables that you will be using in your main circuit. So as the value of different parameters, you can use constant values, you can use integer decimal values, and you can also use algebraic equations to define the values of different parameters. But when you use these algebraic equations, you can see inside this red box, you'll have to put them inside the single quotation marks. Otherwise they will throw you some errors. So you can use algebraic equations, but you'll have to put them inside the single quotation marks. And then you can use different functions. For example, you can use square root, absolute, and any other trigonometric functions like sine, cos, tan. All those functions, they are already defined inside this HSPICE tool, so you can use those functions, but again you will have to put them inside that single quotation marks. So there are two options to include this list of parameters. You can list the different values of parameters using this dot param command in the input.sp file. But if you have a long line, a long list of parameters, maybe thousands of parameters, then you see the .sp input file will be difficult to read, right? So what you can do, you can create a separate file for including the list of parameters, and you can then include that parameter file on the top of the .sp file using the .include command, right? So that will make your .sp input file, the main input file, cleaner and more readable for you, and also if you shared that file with any other collaborators, that will be more readable to them. So that's one of the better practices for listing parameters in a separate file and then including that file using that .include command. And again, these are the options that you can use to define the value of a parameters. As I mentioned, you can use constant real number, you can have integer or decimal number there, you can use algebraic expression, predefined function, which again you'll have to put them inside the single quotation mark that I mentioned. You can define your own functions and you can use that to define the value of any parameter. Again, you'll have to use that single quotation mark to do that. Again, you can use circuit values like voltage of different nodes, current flowing through different components to define a parameter using this dot param command. And again, you can use some values from the external models that you are importing with that dot include, dot lib, dot hdl commands. You can use some values from that models to define some parameters in your .sp file. Then again, I mentioned HSPICE has all the basic functions built in inside it. So these are these are some of the trigonometric functions which are available, and this list goes on, and you can have a look at the HSPICE manual where you have the complete list of all the built-in functions in HSPICE, and you can use those functions to define the parameter values. As I mentioned, you can also use them to define the values of different voltage current sources inside your main circuit. Then you have all the scaling factors here as well, which we use in our pen and paper analysis. So all the scaling factors are same in HSPICE. There's only one difference here. If you remember, in our pen and paper analysis, we use small m for milli and capital M for mega. And as I mentioned, HSPICE is case insensitive. So if you want to use that same convention here, HSPICE will not be able to differentiate between them, because small m and capital M will be treated as the same in HSPICE. So what we'll have to do is, here for milli we can use small or capital M, but for mega we'll have to write MEG. So this is the only difference from the conventional scaling factors, and for other like kilo, micro, tera, all those things are same. You can use just scaling factors to define this multiplying factors in HSPICE. Then, as I mentioned, the HSPICE has the built-in commands to different electric components, and for example, you have diode, resistor, capacitor, all the dependent and independent voltage sources here built in. But you'll have to name them properly to tell HSPICE that this is diode or this is a resistor. For example, if you want to define a diode, the name of that component must start with D. So after D, you can write anything, but the first letter of the name of that component must D if you want it to be a diode. Similarly, you have all the dependent voltage and current sources, which must start with E, F, G, A's based on what you want to use. For current and voltage sources, the name of the component must start with I and V respectively. For resistor, the name must start with R. For capacitor, it is C, and for inductor, the name must start with L. And and the one more thing is important here is if you want to, again, when you use external models and external sub-circuits, when you try to call them or define them in the main circuit, you will have the name of those components must start with X. So after X, you can write again anything, but the name of those external models and external sub-circuits must start with X. And what will be what is important here, if you define these electric components properly, the HSPICE will be able to understand what component you are using. So they will be able to import from their library what is the unit of this component, what is how this component works. For example, if you define a resistor with a R, so it will be able to understand the unit is ohm, and also the current voltage relationship of a resistor is already defined there. So you'll have to name properly in your when you build the main circuit using these different components. Then we also have a dot option command here, where you can define the simulation environment to run any analysis. So HSPICE has like lots of hundreds of option commands that you can use, and each of them has different meanings, different uses. But in our circuit simulation, we typically use these specific option commands, which are mentioned in the left table here. I will talk about these option commands one by one, and I will tell them what is meant by which option command and what each of these option command does. So I'll talk about them. So let's start with the post command. So in the post command, you have four different options. You can use 0, 1, 2, or 3 as the post command. So if you put post equal to 0, the ACSpice will not generate any output file. So that's the we don't actually want that, right? So we do some analysis, some circuit simulation to get the output. So we cannot put post equal 0. And then we have three options. We can put post equal 1, 2, or 3. So if we put post equal 1, the output file format will be in binary. If you put post equal 2, the format will be ASCII. And if you put post equal 3, the format will be binary, but there will be a sophisticated file where the size will be huge. That's why we always use post equal 1, which will create an output file, and the format for that will be a binary. Then we have this probe command. Again, for probe, you have two different options, probe equal 0 and probe equal 1. So if you put probe equal 0, that actually deactivates this probe command, because HSpice, as I mentioned, for any simulation, generates the voltages of all the nodes, current flowing through all the components as outputs. But if you put probe equal 1, it will not generate all the voltages of the nodes or all the currents in the circuit. So what it will do, it will only generate outputs for those voltages and those currents that you have mentioned after that dot print and dot probe command that I mentioned. So that's, and again, we don't want that. So we typically put probe equal to 0. But if you have a big system to simulate, maybe with millions of nodes or thousands of nodes, and if you put probe equal 0, the IC will generate the voltages of all those nodes, all the currents in that circuit, and the output file will have a huge size, right? And that will be extremely difficult to handle that output file. And in that case only, you can put probe equal to 1, and you can use that dot print and dot probe command to print or to output a specific voltage and currents that you are more interested in. Then you have this run level command, which tells HSPICE the accuracy level that you want. So you have you can use 0 to 6, any number in between. So 0 means the it has the lowest accuracy, and 6 means the highest accuracy. So in our case, we always put run level equals 6 to get the highest accuracy. But if you don't put any number in this run level option, the HSPICE by default will consider a run level equal 3, which is the medium level of accuracy. Then you have this in gold option, which tells HSPICE the format of output numbers in the output files. So in HSPICE, you have three different formats: engineering format, which is in gold equals 0. We have this fixed and exponential format, which is in gold equal 1. We have this exponential spice format, which is in gold 2. So you can use any of these formats, and you can actually change the in gold option according to that. But in our case, we always use in gold is equal to 2, what you can see here. Then you have this method option. So here we tell HSPICE the numerical integration method that we want to use for the transient analysis. So here you have three different options. You can use trap, gear, or BDF. These are the three methods available. So if you put method equal trap, that means that will select the trapezoidal rule integration method, and that's typically used for LC oscillators and some analog circuits. And if you like simulate some of those circuits, you can then use method equal trap. So if you put method equal to gear, that can be switched between trap and VDF methods based on the circuit that is similar. And VDF means the backward differentiation formulation method for integration. So that's what we typically use. That's why you can see method equal VDF, and you can again change this method option depending on the circuits that you want to work on. Then we have this misfile and misform option. So misfile equal 1 means the all the measurement results will be printed in one single file. And this misform 3, misform equal 3 option actually generates this measurement result file in Excel format. So these are the two options you can use to generate only one file with all the measurement results. And if you want them in the Excel format, to use them in Next in with Microsoft Excel or any other plotting tools, you can use this misform equal 3 command there. Then you have this CO option, which defines the column width of the printout file in the output. And then there you can have any number between 80 and 132 that will define the column width. And here we always use the maximum number, maximum column width that we can have, which is 132. And again, you can change that to any number from 80 to 132. Then we have this Monte Con equal 1 option, which is for Monte Carlo analysis. So you can always activate this option, but whenever you run any Monte Carlo analysis, then only then this option will come into the effect. Otherwise, it will not affect anything. So you can always put that there. Now I'll talk about how you can define different electric components in the .sp file. So as I mentioned, for having different components, the naming is important. As I mentioned, if you want to define a resistor, the name of that component must start with R, and then you can have anything. So we are defining a resistor called R1, which is in between two nodes, N1 and N2. So you'll have to mention those two nodes, and then you'll have to mention the value of the resistance. Here we are defining a 10 kilo ohm resistance. That's why we mentioned only 10K. And then for capacitor, the name must start with C, and then you'll have to mention the two nodes that the capacitor is in between. Then you'll have to mention the value. Here we are defining a 10 microfarad capacitor. Then you can define DC sources like voltage and current sources. You can have both independent and dependent sources. Here I'm only showing how to define the independent sources. So for example, if you have a voltage source between N1 and N2 nodes, we'll have to again name them properly. The name must start with V for voltage source and I for current source. And for voltage source, we'll have to first mention the positive node. Here you can see that the N1 is the positive node and N2 is the negative node. That's why N1 comes first and N2 comes later. And then you'll have to mention the value of that voltage source. Here we are defining a 0.5 volt voltage source. That's why you can see 0.5. And then for current source, as I mentioned, the name must start with I, and then we'll have to mention the two nodes. Here we'll have to follow the arrow of the current source. So you can see the current source that we are defining here. The current is flowing from N1 to N2. That's why N1 must come first, and then we'll have to mention N2. But if we have a current source with a reverse direction, like flowing from N2 to N1, then we'll have to mention N2 first and then N1. And after that, we'll have to mention the value of that current source. So here we are defining a 5 milliampere current source. That's why you can see 5 milli as the value. And instead of using constant voltage or current sources, you can have piecewise linear or pulse signals as the voltage or current sources here. So to define a piecewise linear, you'll have to use this PWL command, and after that you'll have to list a time value, this type of sequence for that piecewise linear function you want, and you'll have to separate them by space here. And to define a pulse signal, you'll have to use this pulse command, and after that you'll have to follow this sequence. So first you'll have to mention the two levels of voltage that you want in the pulse signals. You might have 0 and 1, 0 or 5 volts, something like that. Then you'll have to mention the delay time, the rise time, the fall time, the pulse width, the period of that pulse signal. And again, you'll have to follow this sequence to mention these numbers in to generate this pulse signal. And as I mentioned, in HSPICE, you can run different types of analysis. You can run DC, transient, and Monte Carlo analysis. For example, to run DC analysis, you'll have to use this .dc command, and then you will have to mention the name of the parameter that you want to sweep. And after that, you'll have to mention the start value, stop value, and the step value in this same sequence. So start, stop, and step. So for example, if you have an inverter circuit and if you want to sweep the input value of the inverter circuit, we'll have to write .dc, the name of the input voltage, which is V in, and then start value, stop value, and the step value. Okay, and another advantage of AC Spice is that you can actually run nested sweeps. So you can have two different sweeps, one after another, and you will get results with all the combinations of those two parameters. So for example, if we want to have the ID/VDS and ID/VGS curves for a transistor, what you can do, we can run this .dc sweep. We can first mention the drain to source voltage sweep, then start stop step, and then the gate to source voltage, similarly start stop step. So this will give you the ID/VDS curve for all these different gate to source voltages. So these two examples that are shown here for DC analysis are using a linear variation or a linear sweep, but you can have other sweep type like decade, octave, and list of points. So for decade, you'll have to use this DSC command, and for octave, you'll have to use this OCT command. And after this DSC or OCT command, you'll have to mention the number of points that you want in each decade or in each octave, which you can see in this example is 10. And then you'll have to mention the start and the stop value for that decade and octave sweep. And for list of points, you'll have to use this POI command, and after that you'll have to mention the number of points that you have in the list, which is 5 in our case, and then you'll have to mention all the values of those 5 points. And then for the transient sweep, again, you can have all those things, but in the transient sweep, you can only, the primary sweep will only be in terms of time. So there you only need to mention the step and stop, because the transient sweep will always start at 0 seconds. So here you can see you need to use this .tran command, and after that we have this 10 nanosecond step time, and then we have this 1 microsecond stop time. So after that, this is again optional. You have this UIC command. So this is to use initial conditions. So in our transient simulations, sometimes we define some initial conditions for the capacitor voltages or inductor currents or all other components. So if you have any types of initial conditions in your circuit, you will have to use this UIC command after this .tran command. Otherwise, those initial conditions will be ignored by HSPICE. And again, as I mentioned, HSPICE supports nested sweep. So after this time sweep in the transient simulation, you can have a DC sweep for any parameters. And for that, you'll have to use this command sweep, and then you'll have to mention the name of the parameters, and then the same format of DC analysis like start, stop, and step. And finally, I mentioned HSPICE supports Monte Carlo simulation. So for that, we'll have to mention this command sweep monte equals some value. So sweep monte equals some value means if you have sweep monte equal 30, that means these will run the same analysis. It might be DC analysis or transient analysis. So they will HSPICE will run the same analysis for 30 times. And for this Monte Carlo simulation, you will have to provide an input distribution, which will have the variation or other informations. And what this HSPICE will do, it will take 30 random values, and it will run the same DC or transient analysis that 30 times with that 30 random values of that parameter that you provided as a distribution, and you will get 30 sets of results for the DC or transient simulation. And this is the Monte Carlo analysis, and I will talk about that in greater details, each of this analysis type in greater details in the code demo section at the end of this video. So as I mentioned, again, you can use any external library, model, or subcircuits in the .sp file. So in this video, we'll use the predictive technology models for FinFETs developed by Arizona State University, and I will show how to include those library in the .sp file and how to use them for different circuits. So now I'll move to the code demos portion of this video. So I will start with the DC analysis. So here we will simulate an N-type FinFET, and we will perform the ID-VGS and ID-VDS sweep in the DC sweep, DC analysis here. So we know that for FinFET, we have 4 terminals: gate, drain, source, and body, which you can see in the left. And then this is the circuit we are going to simulate. So this is straightforward. We are connecting a voltage source to the gate, which is our gate voltage, and we will sweep this to get the IDVGS curve. We have a voltage source connected to the drain, which is the VD, and we'll sweep that to get the IDVD curve. And then we have this body connection to the ground. For FinFET, the body is always connected to ground, and then we also need to connect the source to ground. But what you can see here, we are actually connecting an additional voltage source, which is actually nothing but a 0 volt. You see, 0 volt voltage source. So this is actually a dummy voltage source, and this is doing nothing. So this is eventually connecting the source to the ground or 0 voltage. But the purpose of using this dummy voltage source is that in HSPICE, HSPICE can generate the voltages of all the nodes in the circuits you have, and then it can only show you the currents through the voltage sources that you have in the circuit. But here we want to see the drain to source current, right? But if we don't have any voltage source from drain to source, we cannot see that. That's why we are using this 0 volt dummy source, so that we can see the current flowing through this voltage source, and that will eventually be the drain to source current for our NFinFET here. And the model that we are using, this is the convention to use that transistor model here. So we'll have to again start the name with X, since we are using external models, and then we'll have to mention the node names in this sequence. So first we'll have to mention the grid, drain, gate, source, and then body. So we'll have to follow this sequence, and then we'll have to mention the name of the model. So if we use NFinFET, we'll have to mention NFET. If we use PFinFET, we'll have to use PFET. And then the next thing is optional, which is the nfin command. So in FinFET, we cannot control the width or length of the device by W or L command, but here we can only control the width and length of the FinFET by changing the number of fins, and this is that command to do that. So typically, if you don't put anything in this nfin command, the HSPICE or this model will assume that there is only one fin. But if you want more than one fins in the FinFET, you can mention that in this nfin equal like 2, 3, or 4, or the any number of fins that you want. So we will simulate these circuits in the DC analysis, and now I will move to the demo code that we have. Demo code that we have, and for that I will assume that I'll assume that we already are in the terminal, and here we are in the HSPICE directory here. So we'll have to create a directory where we'll have to put all the necessary files. If we have any external models, external libraries, or external circuits, we'll have to put them here. You can see this is my directory, and this ptmmg is that folder where we have all those predictive technology models for the FinFETs that we'll be using. So this is my library folder, and we'll have to you can put that in any other locations as well, but it's always easier if you put them in the same directory. So this is my library folder, and then for DC demo I have this dcdemo.sp file already created. So to open this file I'll have to use this gedit command, then space, then I'll have to write the name of the file, dcdemo.sp, and then ampersand, and then if I press enter it will open the already available dcdemo.sp file. But if you don't have already created that file, then you can create a new file and you can write the exact same command. So what it will do, it will create a new file under this name that you defined here, and then it will open that file. So since I have already that file, let's open, and it will be open in this folder here. You can see that. So as I mentioned, this is our DC file, and as I mentioned, the first line of the .sp file will always be a comment. So here we are using bunch of stars to define that this is a comment line, and then here you can see we are defining the library that we are using for the FinFET. So this is the folder where you have the models, then this is the models file, and inside this models file we have different technology nodes for the FinFET. So in this demo we are using 20 nanometer FinFET, and for every technology in this predictive technology model we have two different versions, high performance and low performance. So we are using the 20 nanometer HP or high performance model for this, and you see that we are using this .leave command. That means we are including the PTM library here. Then again we have all these options that I have already explained before. So you have all these options here to define the simulation environment, and then you see here we are defining all the simulation parameters. So the first parameter is actually the VDD, where we are using 1 volt, and then we have the VDS parameter for the drain to source voltage. Then we have this gate to source parameter for the gate to source voltage. So we will vary this VDS parameter and VGS parameter to get this IDVG and IDVD and IDVDS and IDVGS characteristics. And then we have this variable called number of fins to control the number of fins for the FinFET that I'll be using. So then we have, you can see this line here, we are calling the FinFET model that we will be using, the entire FinFET. So where you see the name is starting with X, and then the drain node, gate node, source node, and body node are there. Since we are using NFET, we are calling the NFET model, and then we are using this nfin command to define the number of fins for the nFinFET. And here we are actually connecting these gate and drain voltages. You see we are connecting a voltage source to the drain here between the drain and the ground, which is the VDS parameter. Then we are connecting this body to ground, you see, and then we have this dummy voltage source which is taking the source to ground again, and then we have this gate voltages which is connected in between gate node and ground, and we have this VGS parameter defined there. So this is our main circuit. We have this FinFET and we have all these gate and drain voltages, body voltages there. Then we will define the analysis that we want to run. Here we want to do the DC analysis. So for that we are using this .dc parameter. So what we will do, we will vary the VGS gate to source voltage. So VGS parameter, this is the parameter name that we want to sweep. And then we have the start, stop, and step, same format. And for here you see we are defining three parameters again. Start equals 0, so we are starting at 0 voltage. We are stopping at the VDD, which is 1 voltage here, and we are using a step of 1 millivolt. So we'll have like around 1000 values from the outputs from this simulation point simulation. And then we have another nested sweep here. You can see after this sweep command you can mention other parameters that we want to sweep. So we are sweeping this VDS parameter as well, and we are using start, stop, step for that. You can see we are starting at 0.5 volt, we are stopping at 1 volt, and the step is 0.1 volt here. So what this .dc command will do, it will do the IDVGS characteristics for each of these VDS values. So we will have like 6 IDVGS characteristics for these 6 different drain to source voltages. So this could be the end of our .sp file, but as I mentioned, we have another advantage in HSPICE here, which is this alter command. We can use this .alter command to do other sweeps as well here, or to change the values of parameters. So you see, up to this point we mentioned the number of fins equal to, right? So up to this point, the results that we'll get will those results will be for 2 fins of the n fin fed. But here in this alter command, we are changing the number of fins to 3. We have another alter command for number of fins 4, and then we have another command for 5. So what these alter commands will do, this will run this same analysis again and again. It will only change the value of number of fins parameter. All the other things in the .sp file will remain same. Only the number of fins will be changed from 2 to 3, 2 to 4, 2 to 5. And that means this .dc command will generate a .sw0 file as the output, and this alter file will create other .sw file which will have extension of .sw1, .sw2, and .sw3, and we will use them to see the results of this simulation. Now again, if we go back to the terminal. Now if we go back to this terminal here, now we'll run the HSPICE or the .sp file in the HSPICE tool. For that, we'll have to write this HSPICE, then space, the name of the .sp file that we want to run, which is the dcdemo.sp, and if we just press enter, HSPICE will actually run this file, and you see HSPICE job concluded. So that means there is no error. If there is an error, it will show that HSPICE job aborted, and if you then scroll up, you will see there are some errors there, and from there those errors you can have some idea what are the errors, and then you'll have to modify the .sp file to correct those errors, and then you'll have to run this HSPICE command again. Now since our file has run properly, we can now go to the waveform viewer tools that I mentioned, wave viewer or Cosmos Scope, to plot these output results and to verify the functionality or to see the results that we are getting. So in this here we will use the wave viewer, and for that we'll have to use this wv command, wv ampersand command, and for that it will open the wave viewer tool here. So this is the wave viewer tool. Now here you have this open waveform which you can use to open the output files that we have, and you can see we are in the same directory where we are running all our simulations. So we run the dcdemo.sp file, and we mentioned it should generate .sw0, and we had 3 alter commands, so it should generate .sw1, sw2, and sw3, these 4 files. So we can open all the 4 files at the same time. So we will just select all the 4 files by pressing shift, and then we can just click OK. So you can see all the 4 files are open. So we'll first look at the nominal condition where you didn't vary the number of fins. We had like 2 fins, right, for the n fin bed. So for that, we'll expand this output file, and we'll have to create on this top level. So when you create this top level, you will see all the nodes that you have in the circuit, and all the voltage source you will see here, and the current will be visible here. So since we are doing the DC sweep, if you remember, we are sweeping the VGS parameter as the primary sweep here. So in the x-axis of the plot will be the gate to source voltage that we have from 0 to 1 volt. And now if we just plot the IV current, if you remember when we explained the circuit, we use this dummy voltage source to see the drain to source current, right? So this IV current, the current of this voltage source should give us the drain current. So if we just double click on that, it should plot the drain current versus gate to source voltage characteristics, and you see you have 6 different curves for here. And if you remember, we also did a nested sweep for the drain to source voltage where we had, say, 6 different voltages. And if you expand this section here, and if you again expand this, you will see that this is the legend here. You have 6 different values of drain to source voltages, and for this you have this 6 IDVGS curves. And when you increase this drain voltage, the on current, the like the current, drain current should also increase. That's what you can see here. So this brown color is for 0.5 drain to source voltage, and the pink one is the highest 1 volt drain to source current. Now, if you go to the SW1 output file, which is for 3 fins, again, if you click on the top level, you will see the nodes and currents there. Again, if you click on the IV current, you will see the results for this. So this is for 3 fins, and now if you just put two plots in one file, you see that for 2 fins we have lower drain currents, and for 3 fins, these are the 3 fins results for this will give us higher drain current, and that's the normal rule. And similarly, if we plot for the other alter commands, like the four fins, here you can see for 4 fins we have far more drain current. Similarly, we can run the results for the 5 fins. Here you can see that again, if you take them to the same plot, you see that for 5 fins we have far more drain current. So this is for 2 fins, this is for 3 fins, this is for 4 fins, and this is for 5 fins. For when you increase the number of fins, that will increase the drain current again. And for each of the number of fins condition, if you change the drain to source voltage, that will also increase the drain current. So these are the results that we are getting. And here in this web view tool, you have all these options. For example, you can use this cursor. At cursor, you can actually go to 0 VGS conditions, and this will give you the off current. When the gate to source voltage is 0, the current that you get, the drain current that you get, that's the off current of a transistor. So these are the off current values for all different conditions. And if you go to the highest VGS condition, which is the VDD 1 volt, and these the values that you are getting is the on current. And you can see that for now for the increase in number of fins, the on current is also increasing. So you can do this off current and on current analysis here. You can also use this measure tool. I will show that in the transient simulation how to use that. You can build different equations to do some analysis or measurement, and you can plot those build equations there. You can also use the cursor to calculate the threshold voltage of the transistor when like to find out at which point it's turning on. So this is, you can see, this is the linear scale plot. And then if you right click on the y-axis, you can select the scale as well. So for example, if we select the log scale, it will convert all the results into the logarithm scale. And from here, it will be much easier to calculate the threshold voltage of the transistor that we are simulating. So that's the overview of the DC simulation. Now we'll move to the next one, which is the transient analysis or transient simulation. So here we will simulate an inverter circuit. So we know in inverter we have one NMOS as the pull down network, we have one PMOS as the pull up network, and they are connected in series. And the gate of the NMOS and PMOS are connected together, which is the input of the inverter. The drains are connected together, which is the output terminal, and the source and body of PMOS is connected to VDD, and source and body of NMOS are connected to ground. So this is the main circuit that we will be simulating. So again, let's move to the demo codes that we have for this simulation. So again, we'll go to the terminal here, and we'll now open the already created transient demo code that I have already created. So again, we'll have to use the same command, gedit command, then the file name, and then space and ampersand. It will it will open the transient demo file that we have here. You can see that. Again, the same thing, we have the first line as comment. We are including the PTM 20 nanometer high performance model that we're using here. We have all the options we have already explained. Then here we have only the parameter called VDD to connect with the source and the body of the terminal of the PMOS. Then we have this again number of fins parameter, and we have an additional parameter here, which is the capacitor value. So at the output of the inverter, we typically connect a capacitor, load capacitor. So here we are using a 10 femtofarad capacitor as the load capacitance. So here again, you can see we are using the same method to define the pfet and the nfet, and you can see the drain of pfet and nfet are connected together to the output node, gates of pfet and nfet are connected to the input node, source and body of the pfet are connecting to this ndd node, which is connecting to this vdd voltage, and then source of the body, source and body of the nfet is are connected to the ground for the nfet here. And again we are using two fins for these simulations, you can see. Then we are also connecting the output capacitance or the load capacitance to the output node between the output and ground, and which has the value of this parameter that we have already defined. And then we have this again another dummy voltage source that we are connecting to this source of the NFET, a zero voltage source, to see the current flowing through the PMOS and NMOS that we have in the circuit. And then we are using this voltage pulse that I have already explained as the input voltage. So we are connecting a pulse signal as the voltage source between the input and ground node, and you can see the pulse. We are using the pass command. Then you have the two levels of voltage that we want, so we are using 0 and VDD for the two levels of voltage. Then you have the delay time, which is 1 nanosecond. We have rise time, fall time of 0.1 nanosecond. Then we have the pulse width of 1 nanosecond, and we have the period of this pulse signal as 2 nanosecond. Now we will run the transient simulation. For that we'll have to use this dot tran command, step stop, right? So in transient simulation we don't need to mention the start because it will always start at 0 seconds. So we are here, we are using a step of 1 picosecond, and we are running the simulation up to 10 nanosecond time. And then you see we have another sweep command here, which is you see here we have another nested sweep. So we are also sweeping the capacitor value. So you can see we are so for now let's forget, like, comment this out. We will not do the capacitor value sweep. So let's first simulate the inverter circuit in the nominal condition with the 10 femtofarad capacitor. Now here you can see we have only one alter command where we are only changing the value of VDD, right? We want to see the effect of a lower VDD on the inverter circuit. So up to this point, the results will be for VDD of 1 volt, and this alter command will generate another TR0 file, right? So this the up to this point, the output file will be .tr0, and for this alter command, another file will be there, which is .tr1. So this .tr1 file will have the results for this 0.7 VDD. So let's save this .sp file and let's go back to the terminal. Here we will now run the transient demo file that we have just created. And if we just run the HSPICE command for this file and just press enter, it will see, you see that the HSPICE job concluded. That means it has run properly. Now again we can go back to the same wave viewer, and here we can create another wave view using this wave view option. So this will create an open plotting area, and there now you'll have to again import the output files for the transient result, right? So you'll have to these are alphabetically arranged, so you'll have to go to this transient portion. Here you can see these are the output results for transient. We have transient.tr0, and for the alter command we have this transient demo.tr1. So these are the two output files I have to import. So when you import them, now first let's look at the .tr0 file. So expand that, click on the top level, you will see all the node voltages and also current through all the voltage sources that you have. So here we are only interested on the input and output, right, for the inverter. So this is the input. You can see this is the pulse signal that we generated. We had a 1 nanometer delay, then we had a 0.1 nanometer rise time, 1 nanometer pulse width, and 2 nanometer period, right? 1 nanometer high and 1 nanometer low, and we had value between 0 and VDD, so 0 and 1 volt. So this is our input signal that we defined. And then if we click on the output voltage, you will see this is the output of the inverter, and you can see it's working properly. For logic 0 input, we have logic 1 output. For logic 1 input, we have logic 0 input. And if we plot them at the same plot, you will see that these are the inverting outputs. Again, you can use different tools that you have here to do the measurement. Again, you can use cursor to calculate the propagation delay. You remember we try to understand the delay between. So for that, let's ungroup them, and then if you add a uh, cursor here, and if you just we know like for calculating propagation delay, we look at the 50% of the input and time delay between the 50% input and 50% output. So you can do that here. If you select, if you take the cursor to the 50% of the input value and 50% of the output value, you will see the time value here. And if you subtract between these two time values, you will be able to calculate the propagation delay. And this is the manual way, and there is another like automatic way here. Sorry, no, not the equation builder. So here you can go to this measure tool, and you will, if you go there, you see there is different functions that you can calculate here. There are lots of already defined measurement tools. So you can just, here you can see, you can click on delay, and these are the 50% options. You can turn mean and max, and then if you just like okay, you will see that the delay between this rise and fall edge, you can see the delay is 42 picosecond. Similarly, you can have delay between like the fall and rise sections by selecting, by modifying that delay measurement tool. Okay. So you can use all these measurement tools to calculate propagation delay and other parameters as well. Now, if you look at the .tr1 file, so let's group them together. Now, if you go to the other .tr1 file, which was for like the 0.7 VDD. Now, if we go this top level and plot the input, you can see the input is now between 0 and 0.7 because the VDD is 0.7. And if we plot the output and if we group them, you'll see that the characteristics is similar. The inverter is working, but only difference is that initially we had input and output between 0 and 1. Now it's between 0 and 0.7 because we changed the VDD to 0.7, right? Now let's go back to the .sp file again. Here if you remember, we had another nested sweep here. If we add this nested sweep, so what we are doing here is we are sweeping this capacitance value that is connected to the load. We'll sweeping this capacitance value from 10 femtofarad to 50 femtofarad with a step of 10 femtofarad. So we are trying to see the effect of this capacitor on the output characteristics of this inverter. So now if we activate this nested sweep and save this file, and then if we go back to the terminal, and then if we run the same HSPICE command again for the same file, you see it ran again properly. Now if we go to the web viewer and if we just update all this yes to all, and then you'll see that you have, now if we, so now let's delete all the cursors. I will make it much cleaner. And if we expand this section, now you'll see that we have the same results. If we expand the output, if the same results for 5 different capacitors value, and you see that as you increase the capacitor value, it actually creates more propagation delay. That means you have more delay with more capacitance values. So you can also optimize the circuit and different circuit components using this type of nested sweeps in transient or DC analysis. So that's the end of the transient analysis. Now what we'll do is we will go to the next analysis that we have, which is the Monte Carlo simulation. So what the question is, why do we need Monte Carlo simulation? So we know that so far we only considered the nominal values of the transistor, right? So we have only one threshold value for the transistor that we used, and that's the nominal value. But you know, if you use the same transistor again and again in different cycles, you will have different threshold values and different characteristics. And even if you have different transistors, you might have for with same dimensions, but you might have different characteristics from different transistors. So these are the variations that we can have from the process or from the fabrication process, right? So we call this process variation. So to show the effect of this process variation on the circuit level, on the working principle or the performance of the circuit, we do this Monte Carlo simulation. So what we do here, instead of using one nominal condition, we actually use a distribution for different parameters here. And then when we run the Monte Carlo simulation, it takes one random value from the distribution every time, and it runs the same analysis, and it gives you different sets of results. So in this Monte Carlo analysis, we will use the same circuit that we used for the DC analysis. You remember we did the ID/VGS sweep. So we'll do the same thing. Or you can see that here we have one additional resistance, which we are connecting to the drain in series. We are connecting a 2 kilo ohm resistor because we will also be able to show the effects of variation in this resistor on the transistor characteristic, ID/VGS characteristics. Okay. So we are simulating the same circuit just with one additional resistance. And as I mentioned, we want to here we need to use a distribution for the parameters. So here we will consider variation in the threshold voltage of the transistor and also in the value of the resistance of this resistor. So for that, we will consider Gaussian distribution. And then as you can see, if we go 3 sigma on the either side of the Gaussian distribution, that typically covers 99.7% of all the values. So for this Monte Carlo analysis, we will actually run 3 sigma Monte Carlo simulation, and I will show you how to define that in the Monte Carlo in the .sp file. So here, what we are doing, you see, we are connecting an additional voltage source here, del VTAs. So we are connecting this to the gate. So what will it do through this voltage source? We will actually include the variation in the threshold voltage, because the threshold voltage is one value, which is the nominal value. Now if we have a voltage source in series with the gate voltage, the gate will see the resultant voltage, right, sum of this voltage. So if we connect a negative voltage here in this additional voltage source, which will be subtracted from the gate voltage, so we will be able to reduce the threshold voltage. And similarly, if we have a positive voltage, we'll be able to increase the threshold voltage. So in that way we'll be able to include variations in this in the threshold voltage of this transistor. So for this voltage source, we will use this Gaussian distribution, and I will show how to do that. And for the value of the resistance of the resistor, we'll again use a Gaussian distribution to show the effect of variation there. So in HSPICE, we already have defined distribution functions. We have the uniform distribution, absolute uniform, Gaussian, absolute Gaussian, and this limit function. So the difference between this Gaussian and absolute Gaussian is that in Gaussian function, you can define the standard deviation or the sigma value relatively, like in percentage. And in absolute Gaussian, you can mention the absolute value of the standard deviation or the sigma in the absolute Gauss function, a Gauss function. And then you see this sigma a variable here at the end, where you can mention how many sigma you want from the distribution, 1, 2, or 3 sigma. So as I mentioned, we run 3 sigma simulation, so we mention 3 here in this sigma command. And again, we can do both DC and transient analysis for this Monte Carlo simulation. And so after those .dc and .tran command, we'll just have to mention the sweep Monte equal val. So in this val, we'll have to mention the number, how many points or how many times we want to run this Monte Carlo simulation. So in our demo, we will use this DC simulation, like .dc simulation here, using this voltage source, additional voltage source for the threshold voltage, and we'll run 3 sigma Monte Carlo simulation for this DC simulation. So let's move to the move to the terminal where we have already created a DC demo Monte Carlo file, and we'll need to open that using this gedit. So the file name is DC demo space Monte dot sp, and then if you space and ampersand, that will actually open the already available DC demo Monte Carlo file you see here. And all the things are same here up to this point. We have all the parameters. You see, only difference here is that we have two additional parameters, one for the threshold voltage variation, DVTAs, that we are connecting between the gate and the gate to source voltages. And you see, we are defining a Gauss, like absolute Gaussian function. Here you can see this is the main value 0. Then you have the standard deviation 3 sigma values, 60 millivolt. So 20 millivolt is the sigma value, and since we are doing 3 sigma simulation, the absolute value of that variation is 60 millivolt, what we are mentioning here. Then we have at this resistance value, which is 2 kilo ohm in the nominal condition. So here in the first simulation, we will only vary the threshold voltage. And then again, we have that advantage of using dot alter command, right? So dot, we will use another alter command where we'll vary both the threshold voltage and the resistance value. So we'll have two output files, one with only threshold voltage variation and another with both the variation in threshold voltage of the transistor and the resistance value of the resistor. So these things are similar. We have this NFET transistor like the DC analysis. We connecting this additional resistance you see to the drain, between the drain and the VDD. And then we have this drain to source volt, body voltage, source voltages, gate voltages. And you can see we only have here an additional uh, voltage source between the gate and the between the gate and the gate voltage. Here you can see, so this is the Gaussian distribution voltage that we are applying. So then so these are just dummy voltage sources, let's ignore them. So here we're running the same DC DC analysis dot DC with sweeping the voltage gate to source voltage, and then you have the start stop step, same command. This is the only thing we are doing additional here. You can see sweep Monte equal 100. That means we are running 100.3 sigma Monte Carlo simulation for this DC analysis. So as I mentioned, this command will run the same DC analysis for 100 times, and every time it will select one random value for the Gaussian from the Gaussian distribution for that parameter, and then it will run the DC analysis for that, and it will store the all the IDVGS characteristics. But it will be extremely difficult to see 100 IDVG curve at the same time. So what we are doing some measurement here. So using this measurement, we can actually calculate the specific parameters that we want. For example, if we care about the on current, off current, and on off ratio, we are doing this three measurement here. So for that, we'll have to use this dot meas command. Then the type of analysis that we are doing. So DC. If we had transient simulation, we'll just mention tran here. And then this is the custom variable name. You can name anything for this. So this on current, you can see this is off current, this is on off ratio. So we know that on current is when the VGS equal to VDD. So that's what we are doing. We are finding that point, finding the drain current when the gate voltage is equal VDD. So this find and when are the keyword defined by HSPICE, and these two IV current and this VNG PDD will come from your circuit. The way you define these two nodes, you will have to change this voltage. So if you had like only G for the gate instead of NG, then you'll have to write VG instead of VNG. And if you had like V dummy, then you would have to use IV dummy instead of IV current. So these two will come from the circuit, but find and when, these are the two keywords you have to use. Similarly, for off current, we know when the VGS equal to like gate voltage is equal to 0, we'll have to the drain current that we get is the off current. That's what we are finding here. And eventually we are just doing an algebraic calculation. We are like dividing the on current by off current, which is a parameter, to calculate the on off ratio. So these are the three measurement results we will get from this Monte Carlo simulation. So we are running 100-point Monte Carlo simulation, so we will get 100 results for each of these three measurement parameters. Okay. And then again, as I mentioned, we have another alter command where we are again varying the resistance. So we are already varying the threshold voltage, and here we are varying the resistance value with the absolute Gaussian, and we are using again 10% variations. You see 0.6K for 3 sigma absolute Gauss distribution we are using, and the result. So from this we will get two output files. As I mentioned, from this we'll get .sw0, and for this alter command we'll get .sw1. So .sw0 will have the results only for the threshold voltage variation, and .sw1 file will have the results for both threshold voltage variation and the resistance value variation of the resistor. So this is the SP file for Monte Carlo simulation. Let's save this and go back to the terminal. And now if we just run this SP file, which is SSPICE command, then DC demo space Monte .sp, and if we just run this file, you see the file, the HSPICE is running, and it will run for 100 times since we have 100-point Monte Carlo simulation. You can see 100 times. So one thing is done, and now it will go to that dot alter command where you will have both variations. You can see it will again run for 100 points. So if you have 1000-point Monte Carlo simulation, it will run for 1000 times. So it will run the same analysis for 1000 times. And you can, if you notice, every time it is actually calculating these three parameters measure from this measurement command. So it is calculating the you see the measurement on off I on current off current and on off ratio of 100 times. And you see that here after this for each of the measurement results, they are also giving you the mean value of the on current and the standard deviation value of the on current. From here you see then you are again having the off current for mean and sigma value, on off ratio mean and sigma value, right? So you can have some idea about the results that you are getting from here as well. And you can also, as I mentioned, the output will be stored in the .sw0 and .sw1. You can use that. So we will do that. So we'll go to the wave view tool. Again, we'll create another wave view and we'll open the now the Monte Carlo output files you mentioned. You see that we have these two SW0 and SW1, two output files. If you only see the first one, go to the top level, again plot the IV current. So if you see that if you it's difficult to see 100 IV curve, but if you look at here, you see that we have like 100 different plots. If you just scroll down, you will see that you have 100 different plots for 100 Monte Carlo simulations of IDVG curve, right? And as I mentioned, and again, since we have them, if we go back to the terminal, since we have the measurement results, we should have this, since this is DC files and we use this miss form equal 3, if you remember, so it should give you in the Excel format. So we should have two Excel files. You see first one is the ms0, since this is DC, so this will be ms. So if you are transient, this would be mt0. So this is one ms0 csv, and you should have another one called ms1 .csv. So I think you have to refresh this. Yeah, you see this output files. Now if you open this .csv file, you will see an Excel file. You will see that here so I'm sorry, so for the measurement results, even if you have different alter conditions, you will have one output files. That's what we actually define in the miss file. I forgot that. So I will put miss file equal 1, right? So if you put most file equal 1, all the measurement results will be stored in one output file. And you can see that here. So this is your first alter. You can see alter equal 1 in the rightmost column F, and then you have this alter 2, which has the second result. So all the alter results are here, and you see this is the index. You will have 100 points. This will be the number of Monte Carlo simulation that you have ran, and then this is the on current, this is the off current, and this is the on off ratio. These are the three parameters that you measure. Now you can export these output results to any, again, simulation tools like MATLAB, Python, or even Origin, and you can create like scatter plot, histogram plot for this output distributions that you are getting. From that, you will again get the mean and sigma values for these three parameters. And you can also use Excel for that to create the scatter plot or the histogram plot. So these are all the possibilities that you can use that you can have using these output files to present the output results from this Monte Carlo simulation. So what we typically do, we typically plot a scatter plot and then histogram plot with the mean and sigma values for the outputs that we are getting from this Monte Carlo simulation. So again, this is the end of the Monte Carlo simulation, uh, and that's all we had for this video. So I think in this video I tried to give you a complete overview of how to use HSPICE to simulate some circuits and do different types of analysis like DC's, transient, and Monte Carlo analysis. And I hope that will help you to learn the basics of HSPICE simulation tools. And again, thank you for watching this video.